In this video, I want to go through a couple examples where we actually calculate the pH of a salt solution. So our first example, we're going to calculate the pH of a 0.246 molar CH3NH3Cl solution. And we're given the Kb of methylamine, which is CH3NH2, is 4.4 times 10 to the negative fourth. And then remember, because this is an equilibrium constant, right, capital K with the subscript B, I don't need to show units. It does have units, but equilibrium constants, we generally do not show them. So the first thing I like to do is just look at what that salt solution is and then determine, is it going to be acidic, basic, or neutral, as we did kind of in that previous example at the end of the last video. So I know that this is going to separate into CH3NH3, and there is a positive charge on that molecule, actually a polyatomic ion. It's on the nitrogen. If you were to do the formal charge calculation, and then Cl minus, which is inert, it's not going to react with water. So this is acidic. So when I actually calculate my pH, I do want that value to be less than 7. If it comes out bigger than 7, then I do want to go back and check my work. So we're predicting that my pH should be less than 7 because CH3NH3 with a positive charge is acidic. It is actually the conjugate acid of methylamine. And then because it's acidic, right, I'm going to be writing my acid dissociation equilibrium equation, which we can just do right now. Right, I'm going to take that acid, I'm going to react it with water. This is aqueous. I'm going to produce hydronium ions, and then my conjugate base, methylamine. Right, because I'm writing my acid dissociation equilibrium equation, I do need the Ka for this molecule. I'm given the Kb for this one. We know that Ka multiplied by Kb is equal to Kw. Right? If I take Ka, I multiply it by Kb, we do get Kw. Remember, Kw at 25 degrees Celsius, which is what we're going to use if I don't tell you anything different, is 1.0 times 10 to the negative 14th. So to calculate my Ka from that Kb, I'm simply going to divide this number into this. So 1.0 times 10 to the negative 14th divided by my Kb is going to give me my Ka, and I'm grabbing my calculator here. Please do the same. And when I divide those, I get 2.3. I do want 2 sig figs on that. It comes out to 2.272727, so on in my calculator. But it's going to round to 2.3 times 10 to the negative 11th. And then because this is a weak acid, we are going to need to make our ice table. So my initial concentration, my change in my equilibrium concentration. Initially 0.246 molar. Again, I'm just getting that right from the problem. Water is a pure liquid. It's not part of my expression. And then initially I don't have any product. We're going to lose some unknown amount that we're going to call x. We're going to gain x. Because my coefficients are all 1 to 1, it's just 1x for all of these. And then at equilibrium, what I started out with minus what I lost. What I started out with, which was 0, plus what I gained, so just x. and then the same here. And then because my Ka is small, right, my Ka is less than 10 to the negative third, we can assume that the amount that's dissociating is negligible compared to the initial amount. So when I set this up to solve for x, I am going to write this just as 0.246. If we were asked to solve for my equilibrium concentration of this acid, I would need to go back and plug x in, but we're only asked to solve for the pH. So solving for x, I have my Ka is equal to the concentration of products on top, so x raised to the first power multiplied by x raised to the first power, so x times x is x squared. And then on the bottom, just 0.246, because we're making this assumption since my Ka is actually very small. So grabbing my calculator again, we're going to solve for x. I'm just keeping this whole number in my calculator from the last step. So instead of using 2.3, I'm using 2.272727 and so on times 10 to the negative 11th. So if you cleared your calculator and you're typing that in as 2.3, your answer might be slightly different than mine. Generally, they're going to round to the same answer though. And when I did that, I got x to be 2.4. Still just want those 2 sig figs. Times 10 to the negative 6. And then x is representing, right, a molar concentration, so I'm going to add a capital M for my molarity at the end of that. And then, again, we're still looking for pH, right? This is also equal to my methylamine concentration, but we don't need that for pH. We just need my hydronium ion concentration, right? Remember, pH is the negative log of my hydronium ion concentration. So I'm just going to take the negative log of 2.4 times 10 to the negative 6. Grabbing my calculator again. I am keeping the entire number in my calculator from the last step. So again, if you're clearing it out and retyping it in, you might get something a little bit different than me. And I got my pH to be 5.63. If you did clear it, you're probably going to get 5.62, and that's perfectly fine. Do you watch sig figs on this? Remember, log values only the digits after the decimal point count, right? This 5 is coming from this exponent. This exponent doesn't count for sig figs, right? If I asked you how many significant digits this number has, you're going to tell me 2, and you're getting that by only looking at this part, right? This does not count for significant digits. That tells me the magnitude of my number. So because this 5 comes from this, that 5 does not count for significant digits. So I need to have 2 after the decimal place because I have 2 significant digits here. So 5.63. My pH is less than 7, which if we go back up is what we predicted because it's acidic. So we don't know for sure that it's right, but we can be fairly confident in our answer. I'm going to do one more, and then please be sure to practice these. You have a ton of them on your practice problems. Watching me do them is not always the same. In fact, it really never is the same as you doing them yourselves. So this time we're going to calculate the pH of a 0.124 molar sodium nitrate solution. And the Ka of nitrous acid, HNO2, is 4.6 times 10 to the negative 4. Again, it is an equilibrium constant, so it's standard to just not include those units. So same sort of deal. I'm going to look at my salt. I'm going to look at kind of the relevant parts. What's the part that reacts with water? Do I expect my pH to be acidic, basic, or neutral? So this is one of the ones we did in the last video where I gave you a list of salts and you had to determine if they were neutral, acidic, or basic. So if this looks familiar, you probably did just do this example. Sodium is inert, group 1A cation. Those are never going to react with water to produce hydronium ions and hydroxide ions. But because this comes from a weak acid, right, HNO2 is weak, be careful not to get nitrous acid mixed up with nitric acid, right? This one is strong. This one is a weak acid. So if I had NO3 minus, it's actually going to be inert. If I have NO2 minus, which I have in this case, it's actually going to be basic. So do be careful. This is a really common mistake, right? That one little number changes it entirely. So I am going to expect my pH, once we do this, the math, to be greater than 7. If it's not greater than 7, then we did goof up somewhere. So we do want to go back and check that work. Because I'm going to write my base dissociation equilibrium equation, right? Nitrite is going to react with water to produce hydroxide ions plus my conjugate acid. I am going to need my Kb, right? This is a base dissociation equilibrium equation, so I need to use a Kb. If we compare it to the one we did up here, right? This was my acid dissociation equilibrium equation, so we set it equal to my Ka. So be sure you're using the right constant. So just like we did up above, right, Ka times Kb is going to be equal to Kw. So if I have my Ka, I can get my Kb by dividing it into Kw. So 1 times 10 to the negative 14th divided by 4.6 times 10 to the negative 4th will give me that Kb. I'm grabbing my calculator here. Please play along. And I got 2.2 times 10 to the negative 11th. I'm just going to move this up a little bit. So we're going to set up our ice table. You guys should be pros at these by now. So my initial concentration of nitrates coming from here, right? It is a 1-to-1 relationship. So if I have 1 sodium nitrite, I have 1 nitrate. So if I have 0.124 molar sodium nitrate, I have 0.124 molar nitrate. Water, don't care, right? Not part of my expression. 0 and 0 minus x plus x plus x. 0.124 minus x. 0 plus x is x, and 0 plus x is x. And then again, just like in the last example, my equilibrium constant is way small, right? Much less than 10 to the negative 3rd. So when we solve for x, we're going to use that assumption, and we're going to have this as just 0.124 molar. So solving for x, my Kb is going to be equal to the concentration of products over reactants. So x times x, both raised to the first power because there's a coefficient of 1, so x squared. And then using that assumption, just over 0.124. So I'm grabbing my calculator again. Just like in the last problem, I am leaving everything in my calculator instead of clearing it out and retyping it in. So if your answer is off a little bit from mine, that's what's going on there. And I actually got a different answer than when I did this earlier, so I'm going to do it again. I am actually going to retype it in. So 2.2 times 10 to the negative 11th times 0.124, and then the square root of that answer. And I get 1.7 times 10 to the negative 6. And I do just want to double check that one more time. Sorry guys, give you a chance to get caught up. Alrighty, I got the same thing again. So be careful on this one. This time x, right, it's representing my conjugate acid, but it also represents my hydroxide ion concentration, right? Remember, pH is the negative log of the hydronium ion concentration. So once you get this number, you can solve for pH a couple different ways. Remember, your hydronium ion concentration multiplied by your hydroxide ion concentration is equal to Kw. So you can divide this into 1 times 10 to the negative 14th to solve for hydronium ion concentration, and then take the negative log of that number to get your pH. Alternatively, you can calculate your pOH, which is how I'm going to do it. So I'm going to take the negative log of this number and I am keeping it in my calculator from the previous step. And when I do that, I get 5.78. Again, do watch sig figs. This 6 is where this 5 is coming from, so that's not going to count, right? Only the digits after the decimal point for log values are significant. So because this is 2 sig figs, I want 2 digits after that decimal point. And then be careful, this is my pOH. One of the bigger mistakes that students tend to make on this is they just circle this and they say it's their pH and they're done. But if you go back up, remember we said it's basic. We want our pH to be greater than 7. So if you circled this number that's less than 7, you should know that it's incorrect, right? We want a basic pH. This is an acidic pH. If it was my pH, right? It's not. It's actually my pOH because X is representing that hydroxide ion concentration. Right? In the previous example, X represented my hydronium ion concentration. So do be careful on this. To get my pH, I'm actually going to need to subtract that from 14.00. And when I do that, I get 8.22. So pH greater than 7, it's basic. I'm feeling pretty confident on that one.